All right. Today we're very happy to have Soichiro coming from Osaka University. Soichiro is going to be here until June 17th, so I encourage all of you to talk to him. He's great to talk to. Has many ideas, and today he will tell us about some of his recent work, in particular on boundary scattering and non-invertible symmetries in 1+1 dimensions.
Okay, thank you for introduction. I'm Soichiro Shimamori from Osaka Universities, and it's a great pleasure for me to visit New York universities and discuss a lot of things. And so today I'm going to talk about boundary scattering and non-invertible symmetries in 1+1 dimensions. And this talk is based on the collaboration with Satoshi Yamaguchi, and he's a faculty staff at University of Osaka. Okay. So these are today's outline of my talk. So the first is we start with introduction and overview, and next we review some basic facts for understanding our work. And finally, I want to explain our work. Okay, so the scattering amplitude is a key physical quantity in quantum field theories. And by using the scattering amplitudes, we can connect the experiment and theories. But in general, it is quite hard to derive the exact S matrix. So here the exact means the non-perturbative. But however, when a quantum field theory in 1+1 dimension has integrability, we can determine the S matrix by the axiomatic way. So that without resorting to an analysis of Feynman diagrams. And so our interest in this talk is the kink scattering. So our kink is, roughly speaking, a massive excitation interpolating two adjacent vacuum. Here the vacuum states are described by state A and state B. And in this talk, we often explain this kink state like this one. So here this green line represents the word line of kink, and theta is the rapidity. And A and B are the different vacuum. Okay. And particularly, we can introduce these two body scattering S matrix. So the reason why we focus on this two-body scattering is that thanks to the integrability, we can always factorize all scattering amplitudes into the product of these two-body scatterings. So in the context of integrable two-dimensional quantum field theories, deriving this S matrix is enough to understand the scattering amplitude.
Is it important that they are distinct buffer, or they could be like a periodic boson and that buffer identified? Like, could it be the soliton of the Saint Gordon or not?
And now at this stage we don't specify the species.
And is the Saint Gordon soliton a kink for you?
Yeah, you can also think at this stage, but later we restrict to the kink coming from the non-boundary symmetry break. So yeah. But at this stage, Saint Gordon is okay. And so yeah, so in the integrable quantum field theories, we have three consistency functions for this S matrix. So unitarity and Yang-Bakus equation and crossing relation. And the main target of this talk is the last crossing relation. So in the next slide, I want to review the crossing relation. Okay, so the crossing relation asserts the these equalities. So to understand these equalities, we see this diagram from two different point of views. So the first one is that the time flows from bottom to top. And the second one is that the time flows from left to right. So these two different perspectives must coincide. So this gives rise to these equalities. But is this equality always held?
How is theta related to theta 1, theta 2 again?
So sorry, theta is theta 1 minus theta 2. So, yeah, so by using the Lorentz invariance, we can always S matrix in terms of the function of theta. And by the recent work by Copetti and Córdova and Komatsu, it turns out that when non-invertible symmetries are spontaneously broken, then the conventional cross-information must be modified like this way. So here, by comparing these expressions from this original one, we have extra factors depending on the quantum dimension of topological defect. So I want to stress that in the case of non-invertible symmetries, the quantum dimensions are all one. So in that case, these modifications gives rise to nothing. But when we consider the non-invertible symmetries, these modifications generally occurs.
Sorry.
Yeah.
On the previous slide, A, B, C, D were vacua, and now
Yes.
they're topological defects.
Yes. Yeah. I will
What's the
explain.
relation?
Yeah, I will explain this point later. Yeah.
You're going to focus on the regular module category.
Yes, right.
So in general, I should think if I am in some phase described by some module category,
Yeah.
then these quantum dimensions would be quantum dimensions in the module category.
So you are saying about the non-regular module category.
Yeah.
Yeah. So in that case, these parts are should be moreover modified. Yeah. So in this expression that we assume as only regular module category, but
It's not as simple as just using the quantum dimensions of the non-regular module category.
yes, right.
Oh.
Yeah. So in another paper by these authors, they consider such a non-regular module category twist.
Basically, this regular module category just means that all the non-invertible symmetry are broken. It's maximally. So in this case, the vacuum are in one-to-one correspondence with the symmetry. Can I ask a question? What's the reason that there could not be a phase or sign?
Yeah. Here.
Yeah.
Yeah. That's very good questions. And yeah, so in this case, we don't assume that there is no anomalies.
Okay.
So if we have anomalies, then for example, in the Z2 case,
Yes.
F symbol is non-trivial,
Mhm.
and then that gives rise to the extra sign.
But in general, what do you mean by no anomaly? You have a non-invertible symmetry. What is your criteria for no anomaly?
So there is a non-trivial fiber.
Okay. So that going to the derivation somehow?
Yes.
Okay.
Okay, so and as my talk title suggested, the main target of this talk is the boundary scattering. And if we have a boundary in 1+1 dimensional spacetime, then we can also define the boundaries matrix in addition to the focus matrix. And so the boundaries matrix is schematically written like this way. So one kink enters into the boundaries, and then another kink is emitted from the boundary. So then the Gaussian and Samochkov proposed the boundary cross-configuration like this one. So this is a very old and seminal work by these authors. But my question of this talk is how should we modify this boundary crossing relation? So in the rest of my talk, I want to answer this question.
You mean when non-invertible symmetry is spontaneous?
Yes, yes, right. Yeah. Okay, this talk is a long talk, and so maybe it is better to summarize our work here. And we assume these two things. So the first one is bulk integrability. And the second one is that the boundary is weakly symmetric under the non-invertible symmetries. Later, I want to clarify the meaning of weakly symmetric. But at this stage, about boundary preserves some symmetry.
Okay, and so,
Yeah.
correct me if I'm wrong, but if I remember well, there was some homological condition. For this reflection condition they proposed, they assume some symmetries in the world, right?
Yes.
It's not the most general one that they can write down, but then they assume some symmetries. This you will support, you will suppose that these symmetries still are preserved, they persist, but you will focus on the case in which non-invertible symmetries are spontaneously broken.
Yeah.
But with these symmetries in the world.
Yes.
So you mean the boundary integrability?
Yeah, for example, yeah, because they assume that, right? So it's, okay.
Yeah, so we assume that both non-invertible symmetry is always.
Just understand which word they are.
Yeah, good.
Okay, a question also about the previous work. So that was all interesting. So that also all assumes integrability, all this,
This
there's
one.
there's no extension.
Okay, yeah, the authors did not assume integrability.
They do or do
They didn't.
They do not.
They
They
do
do
not.
not, okay.
Because this is just the 222.
Right, yeah. But I don't know if they somehow in proof, I don't know if they use.
No, the proof is based on some kind of just understanding the normalization of the states.
Right.
Yeah, so to derive these external factors, we just rotate two body scattering like this. So then there is no room for assuming symmetric values. Yeah, I want to clarify. Yeah, that's point right.
Oh, but so related to Gaston's question, then on this slide where you explain the assumption, you are not assuming boundary integrability, are you?
Yes. Yeah.
You are not.
Yeah, we not
Okay.
assume the
Okay.
boundary.
It's only assuming both.
Yeah.
Thanks.
And so, yeah, under these two assumptions, we find that the boundary crossing relation must be modified like this one. So here is comparing to as a conventional boundary crossing relation. Here is one, but we have some non-trivial modifications appear here. Okay. So this is what I want to show in this talk. Okay, but before the main part, I will give you some intuition why the crossing relation is modified. So to understand this, firstly, we record that how can we compute the scattering amplitude. So to derive the scattering amplitude, we can use, we always use the LSC reduction formulas. So the LSC reduction formula connects green function with scattering amplitude. And so, yeah, in the framework of quantum field theories, we can compute these green functions. And by using LSC formulas, we can translate these green functions to the scattering amplitude. But here we'll revisit the LSC reduction formula. Yeah, again, we consider the two-body scattering denoted like this. And so here that we don't specify the dimensionalities. So now that this H matrix generally depends on Mandelstam variables S and P. And so then the LSE reduction formulas for this two-body scattering can be written like this. So this is green functions for these for point functions, and to amputate these external lines, we introduce this kind of factors depending on the moment. But I want to ask, is this formula always correct? And the answer is no. So this is very crucial. So to see this, let's briefly look at the amputating process, so namely normalization process. So typically we amputate the initial external lines. So here the force we consider the amputating for these external lines. And in the amputating process, we consider this kind of 4-point functions. So this can be a schematically written like this. Okay. So in the framework of LSE reduction formulas, we always assume that these two points are space-likely separated away. So then this 4-point function can be split into these two green functions.
That, what is this part? It's not Fourier transform, right? In space-time.
Sorry, this part is a Fourier transform.
But in space or in space-time?
Space-time.
Space-time. So what does it mean that they are space-like separated when you integrate over time?
Sorry, that's very good. Yeah. So okay. So yeah, to be more precise, we should discuss these discussions in a positional space. But here, maybe even most of you are familiar with this momentum form. So I brought this, but yeah, yeah. But we can of course move to the positional space and discuss the similar things.
We can move to the LSE formula written in terms of limits for large and for initial and final time, right?
Yes.
But then to write it in that form, you have to rewrite the Green's function as an integral of whole space time.
Yes.
For T order functions. So I don't know in the second context here, what does it mean, space like time line? How can you tell?
Okay. So okay, to be more precise, we must perform the Fourier transform this diagram, and then going back to the position space, and then we can define the location of these 4 points. And so yeah, in the position space, we can justify this limit. But these splitting properties is common to position momentum space. And we can always perform the Fourier transformation and back to the position space. And so these parts are plays the role of amputating initial external lines. And so this part corresponds to this one. And so the discussion so far assumes that the scattering particles are described by local operators. So if we are familiar with conformal field theories, this means that the scattering particle state belongs to the anti-Soichiro space. So in this case, LSE formula is always correct. But in quantum field theories, we also have non-local operators. For example, kinks. So in these non-local operators, some topological line defects are attached. So here the local operator is just point-like operators, but for these non-local operators, this topological line defect is attached to some local operators. So in this sense, I use as a non-local operators. So when we consider as a scattering for this kind of scattering particles, then this LSC formula may be modified. Okay, so to understand this, we again consider the amputating and normalization process. So historically, the amputation has been performed by these 2-point functions for initial state. So this is a complete analogy for this one. But to obtain the correctly normalized S matrix, the amputation and normalization should be performed by these 4-point functions.
What do the blue lines represent?
So blue line means topological lines. So this is a kink word lines, and 2 kinds of topological lines.
But they are different, right? The blue segments are different topological lines.
In general, yeah. Yeah. But these 2 kinds of amputations are different when the scattering particles are associated to twisted sectors. So namely, this 4-point function isn't equal to these 2 bubbles. So this should be contrasted with the scattering for untwisted sectors. So in the case of untwisted sectors, these are blue line. The blue lines are don't appear here, and so we can separate these 2 lines, and this equality does hold. But when the twisted sectors are concerned, this equality no longer holds. Okay. And yeah, so historically, as amputation has been performed by G, but the correctly normalized S matrix should be performed.
Yeah, it's important. It's good that lines are for dimension 1. That the
Yes.
like higher dimensions will know.
Yes. So yeah, we consider the particle scattering. So this topological line is always.
I'm just wondering, like in QD, we also the electron is created by something that does attach the Wilson line, but it's not for dimension 1. We don't worry about this stuff.
Yes. Yeah. So yeah, like in this figure, I always assume the 2 dimensions.
And also here is also where anomaly could make a difference, right? Even if it's invertible, anomaly would, if the symmetry has anomaly, then it's not going to be equal either.
Yeah. Right.
It'll be a phase.
Yeah. Right. Yes. Right. And so yeah, so these 2 discrepancies give rise to the modifications of crossing symmetries. Okay, so based on these observations, these authors found the modified crossing relations.
So the related to Gabriel's question, I mean, in 2+1 dimension, when you consider transcendence matter theory,
Yes.
The scattering of these anyons, which are like electrons attached to Wilson lines, they also appear to have a modified crossing relation.
Maybe I will.
Can that be understood also in terms of some picture like this?
I'm not sure.
But you're aware of this modified crossing relation, right? From like Miwala and friends, and also from Xing and friends.
Yes.
Maybe something I can ask afterwards.
Yeah. I'm not sure.
It's not the same argument.
Yes.
For sure, but
I'm not sure about it. So next, I want to review the non-invertible symmetries and kinks. And yeah, so these two relations are developed by these papers. So these are just partials. So the non-invertible symmetry is non-group fusion rules. So when we consider the invertible symmetry, all topological line defects obey the group-like fusion rules, but non-invertible symmetries obeys the non-group. So mathematically, the categorical fusion rule. And throughout this talk, I assume this kind of fusion rules. So multiplicity free, so namely that this fusion coefficient takes 0 or 1. And yeah, so there are many important facts for non-invertible symmetries, but as far as today's talk is concerned, this partial fusion is enough to understand our result. So the partial fusion ensures that if we parallelly place these topological line defects and perform the partial fusion here, and then this partial fusion gives rise to the sum of over LC with this extra factor. And we assume that this fusion category is preserved along with RG group. So that we consider the UV CFT, and by adding the relevant deformations, that this UV theory flows to IR theory. But deformation operator commutes with these topological line defects. So then,
do you also have the null line among those cells? Do you also have the null line among those cells, the trivial line?
Yeah, I include yeah, topological trivial topological. So yeah, so this is the assumption. And we also assume that non-invertible symmetry is spontaneously broken. So then we have a degenerate vacuum, which is described by state A. So in general, this vacuum state belongs to the module category. But now that we assume that this vacuum state is an object of regular module category. So in this case, we can express this vacuum state as an image of element. So by using this vacuum, we can characterize the kink between these two defined states. So this is a random incident potential, and at the bottom is described by vacuum state A and A plus 1. And so then we can define the kink across in this part. Okay, so here it's better to give the simplest examples for our scenario. So the simplest example is tri-critical identity. And tri-critical identity has two kinds of non-invertible categorical symmetries. The first one is Fibonacci, and the second one is Tambari-Yamaguchi categories. So here that we deform this tri-critical identity by the primary operator epsilon prime with negative sign. So firstly, that we show that this primary operator commutes with all topological ones in Tambari-Yamaguchi categories. So from this, we can say that this deformation preserves this Tambari-Yamaguchi category. So then the IR plate of this deformation is gapped place with 3 degenerate vacuum. So this is corresponding the random incident potential and each bottom is equal to the value, and each value is related to the topological lines in Yamagami category. Oh, yeah, so in this case, we can consider the two kinds of kinks and anti-kink counterparts.
So earlier you said you were restricting to non-anomalous symmetries.
Okay. So at this stage, we don't use such anomaly properties. Yeah. So when deriving the crossing relation, such information is used.
But the crossing relation also holds in the case when the symmetry is when the symmetry category does not emit the Faber functor. You said it was when it was derived, the crossing relation when it was derived, it was used the symmetry as a Faber functor.
Yes. Yeah. So yeah, we employ these anomalies as we employ that with the definition of anomaly, but
So you can't use the crossing relation you derived doesn't apply to the example on the previous slide, right?
yeah.
Which crossing relation?
So these
This does not apply when the symmetry does not emit the Faber functor. It applies, right?
yeah. So in this expression, that we assume that there is no anomaly.
But the icing has, does the Tamura-Yamagami symmetry, icing category symmetry, does it have anomaly or not?
Yeah. Right. Yeah.
So this does not apply to icing, or applies to icing? I thought the derivation probably just used the crossing relation,
Yes.
right? Sorry, the crossing relation for the topological defects.
Yeah. Right.
That relation you wrote does not rely on the symmetry having anomaly like that.
So the important point is that So for example, when considering this S matrix, then okay, so the amputation of this initial two kinks is related to the amputation of this one by FC. So then when there is anomaly, then epsilon factors appear.
Actually, I don't understand. Even if there's no anomaly, there's still F symbols. Like in the non-invertible case.
Yeah.
So shouldn't they show up? Or?
Okay. So okay. You are saying about the anomaly for non-invertible symmetry.
Yeah.
Okay. In that case, I'm not sure. Okay. So
So the previous formula certainly applies. It was claimed to apply for general, like including icing category symmetry, right?
Yeah.
If your definition of anomaly is that it has no Faber functor, then that's also anomalous.
Yes.
So that's not what you meant. Like the crossing equation with the quantum dimension factors. That applies under some other condition. It does not apply when the symmetry is invertible but anomalous. But it applies when the symmetry is non-invertible.
Yes. Okay. So yes.
So is it no? Like this crossing relation, like either the previous one, this one, or the one you wrote for boundary, under what condition does it apply?
Okay. So
of the symmetry. So
in deriving this modification of crossing relation, we are it is enough to assume the spontaneously growth of non-invertible. And in that case, this non-trivial modification occurs.
I see. For just for the completely broken. So even if the case, if you consider like anomalous Z2, if it's completely broken, then this is fine. There's no -1.
Okay, so in the case of invertible symmetry is anomaly.
Yeah,
Then instead of this,
yeah.
we have extra factors.
No, but how do you, how can you tell the difference intrinsically?
Okay.
I mean, if there's extra factors
Yeah.
even in the invertible case with anomaly, why wouldn't there be extra factors all the time in the non-invertible?
Because you can put them together. for example.
Okay. So intrinsically,
Yeah,
to obtain computations
yeah,
for initial kink space,
yeah,
we consider the inner product
mhm,
of these two products.
yeah,
But when time flows
yeah,
from left to right,
yeah.
then the initial kink stays.
I understand, yeah.
And so this computation process is related to the FC.
That's right.
So yeah.
So, we're just asking, like, under what condition this relation between these two diagrams is related by something that's positive. Positive, just determined by the quantum dimension. Because sometimes, as you also mentioned, if the symmetry is invertible but anomalous, this relation will involve a phase, which is sensitive to
Yes.
anomaly.
Yes.
But that's not present in the formula you presented.
Yeah.
The formula you
So when
presented.
is the formula true?
Yeah, when is the formula true?
Yeah, could you just say like.
Yeah,
what the
abstractly,
conditions
if is there a condition on the fusion category symmetry here under which the formula is true, at least believed to be true.
Formula.
Yeah, the formula that you had. So this formula includes the case of invertible and anomalous free symmetry.
Yes.
Also includes cases like icing category. And the question that we're asking is under what general condition on the fusion category this formula is believed to be true.
Okay. So
We know cases where it's true, with cases they're not true, but we don't know what is the general kind of intrinsic condition you put on the symmetry for this formula to hold.
okay.
I thought maybe you want to say this is true if you have any fusion category symmetry and you just assume that the symmetry is fully broken.
Yeah.
But I don't know if that's the right answer. That's what we're asking. It doesn't sound like the right answer because it doesn't play well with the anomalous case.
Yes. Yeah. Yeah. When my matrix symmetry is anomaly, then I'm not sure this formula works well.
No, but you have to define what you mean by when the non-invertible symmetry has anomaly.
I mean, but also like
Yeah.
if you were just applying this to invertible symmetries, then you presumably wouldn't even write any expression involving the quantum dimensions, right? Because they're all
Yeah.
one. So presumably they have in mind that it applies to some non-invertible symmetries.
Yeah.
But somehow I don't like in the invertible case, you can say if there's no anomaly,
Yeah.
there's no F symbols, but in
Yeah.
the non-invertible case, there's just always F symbols. So I don't. Yeah, I guess.
Okay. So yeah. I'm not sure about the anomalies of non-invertible symmetries in this case.
But you are claiming that it holds if there's a fiber factor. So you're
Okay. So
that's never used in the
yeah.
The boundary condition here is not the fully symmetric one.
yes.
Yeah. I have never used such conditions.
Maybe we can discuss afterwards.
Okay. Yeah. Okay. We move to the boundary scattering, and this part is a review part by the paper of Córdova and Komatsu. So if we allow the boundary into the space-time, the scattering data consists of these two S matrices. So the first one is bulk S matrix, and the second one is boundary S matrix. And we believe that this bulk S matrix should not be affected by the boundary. And so our target here is the boundaryless matrix. And recall that the bulk S matrix must be subject to several consistency conditions, such as unitarity and Yang-Baxter and cross-correlation. So in the same way, Gaussian and Samochkov proposed the three consistency conditions for boundaryless matrix. So the main target of this talk is the boundary crossing relation. And our boundary crossing, a boundary analog of crossing relation is more non-trivial. And so I want to review how the Gaussian and Samochkov arrive at the boundary crossing relation. So to understand the boundary crossing relation, we first move to the rotated picture. So namely, in this picture, the time flows from left to top. And by rotating this picture, we can consider the another boundary S matrix, which is described like this. So here there is a very important point, and so in the pre-rotated picture, this initial kink state belongs to the Hilbert space attached to the boundary, and the final state also belongs to the Hilbert space with boundary. But after rotating this picture and considering this diagram, initial these are final two kink state belongs to the bulk Hilbert space rather than the Hilbert space attached to the boundary. This is because there is no this space line does not anchor to this boundary. So and time evolutions is performed by the bulk Hamiltonians. And so these initial and final states belong to the bulk Hilbert space. So then since this Hilbert space is bulk Hilbert space, so just by inserting complete set of asymptotic states here, then we can obtain this kind of relation. Yeah, so this insertion is justified only in the rotated picture. So here we should remark one important comment. So in this expression, we used and assumed as a bulk integrability. Because if we don't assume the bulk integrabilities, merge kink contributions appear here. So in that case, there are many terms in addition to this. So to suppress such a merge kink contributions, we assume the bulk integrability. So to sum up, the boundary crossing relation can be put as follows. So the first one is obtained by rotating these pictures. And the second one is what I said in the previous slide. So by plugging this as a first equation into the second one, then Gaussian and Samochkov arrived at this expression. But we question that is this equality false or not? And we find that this boundary configuration is necessary to be modified when non-invertible symmetry is spontaneously broken. So finally, then we move on to our work. So how should we modify the boundary configuration? So as I said previously, that we assume two things. So the first one is bulk integrability. And this bulk integrability is necessary to suppress much kink contributions. And the second one is that the boundary is weakly symmetric under the non-invertible symmetries in the bulk. So the meaning of weakly symmetry is that there is a non-trivial topological junction like this. So this means that this is a boundary, and this is the topological line in the bulk, and there is some non-trivial topological junction here from L times B to B. So this is the meaning of from L times B to B. So this junction is topological, so we can freely move this junction as a bulk topological. So first reason which we note that in the rotated picture, the correctly normalized matrix, boundary S matrix must satisfy this relation. So I want to emphasize that this equation is so rigid, so there is no room for modification for this equation, because this can be obtained just by inserting the complete set. So this equation cannot be modified. But instead of this, these two boundary functions are different.
Can you explain the difference? What does this question mean?
The letters are different.
Yeah, but what is the second letter?
Second,
The second. I understand there are two kinds of R. What is the second kind of R?
sorry. I thought you. I thought you. Okay, so. Okay. So, yeah. Yeah. So. Yeah. So. Yeah. How to say? Yeah.
So you're proving by contradiction, right? You're proving
Yeah,
they're
yeah,
the same.
Right.
Then you get the contradiction, and then so this has to be not the same.
No, but what is the second? So the second R is the one that refers to the rotated picture, maybe. Sorry, right?
Yeah. So I wanted to say that this is correct.
Okay.
And this relation is modified by some.
Yeah. Sorry, I think I was
Yeah, just
not
how
paying
is it-
enough attention
yeah.
to which R was which, so I don't know what the first solution means.
Can you first kind of remind us what was the separate definition of the second R?
Yes. You probably did in some previous slide.
The previous slide.
Yeah, just rotated.
Yeah.
Before.
I think must have been
It's
before.
in the boundaries in the time direction, right?
Yes.
Okay. Yeah. Sorry.
Yeah.
Maybe a different notation would help. Like R, like this way, and then I rotate it.
I think it should have been word at this stage.
Yeah.
Okay, sounds good. Okay, thanks.
Yeah. So
Okay.
So yeah. The reason why I use this symbol is that this R matrix is a map from human space with boundary to human space with boundary.
Understood.
But in this case, this R matrix is a map from bulk human space to bulk human space.
Is it a map from bucket space to bucket space, or it's just an initial condition?
So sorry, now that time evolution is performed by the bulk habitat.
It's overlap in the boundary state and then this pair of.
Yeah.
Yeah,
Okay.
These are difference of variable spaces, right, strictly defined from the bulk of its multiple space. So, that's why I changed.
Yeah.
these lines.
Sorry, I still don't understand the second picture.
This one?
I know. One more slide back. Yeah, the second picture here.
Yes.
How do I extract a number from this?
So think about the overlap between the boundary state and the other state specified in and out state.
Yeah.
Okay.
Those are out states, right?
Yeah.
Yeah.
Oh, I see.
Yeah. Yeah, so this picture can be thought of as the boundary produce the kink and anti-kink pairs. Right. Okay, to find the proper relation here, we must carefully look at the normalization of
I think now, I don't really understand again the derivation of the first equation.
this one.
Yeah.
Yeah.
So because now it's the same R.
Yeah.
Yes, right.
So yeah, so this is with no reference to the.
There's no rotation. Yeah.
There is no crossing here.
Yeah.
You're just saying that.
Yeah. Just insert complete set of states using
Yeah.
bulk integrality.
So
Yeah, exactly. Okay, there is no cross.
yeah, no cost. So there's no room.
But here I thought you would use the curly R, not the.
No.
Wasn't,
Oh. No.
isn't the left picture the curly R?
Really?
No, it's.
What?
I
Can you go back?
think it's the.
Can you go back one?
Yeah.
Oh, okay, sorry.
Yes, yeah.
Okay.
Carrier is a rotation.
Okay,
But it's
sorry.
yeah.
But the shift in theta in this equation came from where?
This one.
The next slide. You got minus theta on the left hand side, theta on the right, and
Yes. Okay. So okay.
because
Okay.
so why you're not integrating over? I'll show you something else. The argument.
Okay. So to derive this argument, we must change the rapidity here. So yeah. So
Just because the theta one cross here, theta two cross there, there's a. The theta is the difference between the momentum, the rapidity of this left and right.
Yes.
But then, through the bulk vertex we cross.
yes, yeah. So yes, theta, and so this is theta,
Okay.
and
I mean, you could have also had a contribution with this matrix at theta equals 0, right?
Yes.
But that's trivial. That's okay. You could have also had a term with S of 0 and momentum would have been conserved.
yeah. Of course, momentum is conserved. Yeah. So here I just used the bulk integralities. Sorry.
You're saying so the
Okay. So this momentum is equal to this momentum.
Just look to theta 0, theta 1, theta 2.
I understand why it's not possible not to have an S of 0. S of 0 is 0.
Oh, you're taking theta equal to 0?
If I take S of, I can have R minus theta S of 0 equal R minus. That's not allowed. So there's something. Oh, okay, I probably I'm the only one confused. So I'll ask you later. I don't want to debate it.
Ah.
Okay.
Yeah.
Okay, so that's why we carefully look at the normalizations for each boundary matrix. So first of all, let's start from these are boundary S matrix in the rotated picture. So the correctly normalized S matrix in the rotated picture is given by like this way. So there is no topological attachment to the boundary. So the boundary inner product is just like this. So this is common to the Gaussian and homological assumptions, but this inner product for that's the inner product for outgoing state is like this. So to reduce this diagram to the to this one, we must perform the partial fusion for these topological lines. So then this partial fusion gives rise to this diagram based on the fusion properties. And so here, in general, we have many topological lines connecting these two bubbles. But if we take the bring these bubbles to the very far away from the one from the other bubble, then the one can expect that only identity line contributes to this summation. This is because that the vacuum here is zero, and when we act LD on zero, then such a vacuum is LD times zero. But this state is also one of the vacuum states here. So this orthogonality ensures that only identity operator contributes to this summation.
I think this is also related to the previous question that we asked. So here, what you're crucially using is actually the symmetry line. This LD has no non-trivial Frobenius Schur indicator.
Yes, right.
Like the expectation value on the sphere and on the cylinder are the same.
Yes.
So I think that probably the crossing relation that you wrote down before and the one you are writing works if the Frobenius Schur indicator of the topological lines involved are all just, if they're not zero, they're one.
Yeah.
I think that's the general criterion.
Yeah.
If there is a non-trivial Frobenius Schur indicator, then it just appears as a
-1. Yeah, the phase are kind of more restricted. Seems. Yeah.
For the mortals, the Frobenius Schur indicator.
Sorry?
For me, for Frobenius Schur indicator, what is it?
It's like the orientation reversal anomaly. So it's a topological defect that looks self-dual. Okay. But if you study carefully, actually there's an anomaly when you flip this orientation. This is related to the cases where the symmetry is anomalous.
Yeah. So in the case of rising on SU2, SU2 SU2 models, most of theories have Z2 lines. Yeah, so in that case, this coefficient is a Frobenius Schur indicator. So
I think what is particular component of F symbol.
Yeah.
I was a bit confused. I got a bit lost in your explanation here about taking these two things far away. That things were like topological. I thought it should matter, but just so I know, is this the exact relation that you're writing here, this final line, or is this an approximation?
Okay. Yeah. So this blue line is topological.
Yes.
But this black point is not topological.
I see, okay, I see.
So in our case, we cannot use the topological cancellation, topological punishment conditions. Because this is not topological.
You were trying to explain why this is not exact equality, right?
Okay, yeah, okay. So, if we set the range between these two bubbles finite, then there may be some superposition of the vacuum 0 and non-trivial vacuum D. But if we separate these two bubbles far away, then such a tunneling effect can be suppressed. So very roughly speaking, this can be approximated by some kink mass times So here the L is the range of these two bubbles. And so this exponential factor is the tunneling effect of the 0 and B. But if we bring these two bubbles very far away, then this terms vanishes.
Yeah, okay. So it's not specifically the D line, I guess, if you just have some line connecting, unless you have identity there, there's some topological line connecting them, so there's some kink that you have to pay.
Yeah.
That you only, okay.
Yeah, right, yeah.
And what Soichiro was explaining also is that if this black dots were to be topological, then you can actually show this approximate sign is actually an equal sign as a consequence of the typo. No typo.
Okay, so this normalization factor can be written like this. So these two inner products are nothing but one used for applications in the used in the Gaussian and the Morse code. But in our case, we have this extra factor.
5 more times, do you?
Maybe 5 minutes. Okay. Okay, so next we move to the normalization of RABC. So the correctly normalized the boundaries matrix in the pre-rotated picture is written like this. So here the normalization factor should be written like this inner product. And then by using the fusion property, we can evaluate this inner product like this. So the logic is the same as the previous case, and only identity wise contribute. But here there is some subtleties defining this inner product. So here we define this inner product like this. So then by using this FB and DB, we can express this inner product like this. So here the GB is the product of DB and FB, and this GB contains some ambiguous numbers depending on the boundary. Okay, so then by using the results obtained so far, we can obtain we can rewrite this pre-rotate this boundary matrix with rotated S matrix like this way. So this is a result of so this is a device of between two pictures. Okay, so as a third, yeah. Then by plugging these expressions into this one, we obtain this modified boundary crossing relation. So importantly, these ambiguous parts can be cancelled in both hand sides because these ambiguous factors depend on B and C, but here CA and CA are C and C appears in the same root, and so this part cancels each other. So then the remaining is this non-trivial quantum function. So this is the main result of our work. So here, let me summarize with some future directions. So we revisited the boundary scattering theory. And we found that the boundary crossing relation should be modified when non-invertible symmetry is spontaneously broken. And yeah, so if you are interested in some concrete examples of boundary scattering, then please check our paper. So these are some future directions. So thank you.
More questions for Soichiro?
You actually just give a simple example where the unmodified crossing holds. I'm just curious what the simplest example is.
So this one.
No, the one without modification.
So
the original one that doesn't involve these quantum dimensions.
But you can just rescale them by square root of dB and dt3.
I just mean like, okay, maybe what I'm asking is, I just feel like
The
in
previous
1 +
solution
1
all satisfy this, of course.
Sorry?
The previous solutions all satisfy this without the prefactors.
Yeah.
And you can obtain those that satisfy this prefactor just by rescaling.
Sorry, I just meant the original Zamolodchikov paper. It's a different formula than this, right?
Without the prefactor.
Yeah,
But if you have a solution there, you have a solution here.
yeah, but yeah, so as far as I know, there is no some reference where the boundary scattering is discussed when the non-invertible symmetry is spontaneously broken. And so yeah, so
You're saying that nobody has actually calculated this are explicitly in the case when the bulk non-invertible symmetry is spontaneously broken.
yes, right. And yeah, and so yeah, so
Because the original paper is for the massive fermion, right? So that's a symmetry
yeah.
preserving phase.
Yeah, I mean,
The logical Gaussian was for massive fermion in the bulk.
okay, that was based on my question because somehow
Okay.
1 + 1D, you generically like are spontaneously breaking non-invertible symmetries if you have multiple vacuoles.
Yeah.
I was just having a hard time imagining how you could have kink scattering without it or something.
I guess it's a related question, but I guess there in the original paper on the bulk scattering, there were some S matrices that were in the literature that didn't satisfy crossing and motivated, right? This fix, or that didn't satisfy traditional crossing. That's why, right? Motivated this.
The 2-2-2.
Yeah. Right.
Yeah.
So were there boundary crossing relations that weren't satisfied, so that you make this fix or something? Were there examples in literature that you did like called out to this fixing, or you just found them afterwards? I guess. I'm just curious. I guess it's still cool.
But the 2-2-2, the crossing was fine. It doesn't play well with the symmetry.
Right. It was like you had to choose. Yeah.
Yeah. But the people, I think, remember people did look like, for example, in the model, not unitary, but you can still talk about this, you know, this in the massive phase and talk about boundary scattering. You can study the scattering for the with the boundary, right?
Yes,
In that case, of course, the symmetry can only be spontaneous broken
yeah.
because of the normal. Presumably that will be one example for a friend of the question. Okay, maybe let's thanks Soichiro again.
Explain again the derivation of the factoring.
Okay.
Yeah. So
Maybe here.
yeah, so here okay, the first step is, so where does the something come in? In the first step that you wrote to the composition like this?
Yes.
So
Yeah,
so
yeah.
so
This
here
first
you
step, yeah.
say
Here
normally you could have more just some.
it could have signs. So here it's purely positive, right?
Yes.
It's purely positive. So there are several subtleties over here. I mean, there's always the choice of basis associated with junctions. If you want the choice of basis to have some nice property under permutation, then this the second equality is incompatible if there's a non-trivial for finisher indicator. So the point is that the second sum is a positive sum.
Yes.
That relies on assumption.
And yeah, and
That's what breaks if the symmetry here are, for example, like anomalous C2.
And sorry, it's because in the first picture, the A line's like going up and then you have to bend it down.
Yeah, that's right. Yeah.
I see. This you're basically trying to resolve a junction.
Yeah, that's right, that's
It
right.
could be ambiguous. Like
That's right. It's the
repetition
first step is
functions.
basically like you have parallel and then you want to bend like this.
Yeah,
That's where the anomaly enters.
I see. Okay.
Yeah, this is why I say it's related to flipping orientation. Like you're bending the line. I mean, it's like the cusp line going from the straight and the bend.
And sorry, you were saying something about the operators not being topological. This is
The black dots are
Yeah.
creating the
yeah, they are not topological.
Yeah.
So the last equality.
the last one is a limit. It's not a strict equality. It's a limit when this two bubbles are far away in transverse directions in space.
And that's enough for the LSZ.
Yeah.
Physically kind of
Because they're talking about
understand.
symmetric phase. Yeah. I mean, it's related to Maxwell's question. I think you were thinking in position space,
Yes.
and then but you write things in the momentum space.
Yeah.
Formula are not quite consistent.
Yeah. So to be more precise, we can write. We can perform the grid also.
Yeah.
And we can discuss.
Okay. Sense.
So you mentioned the bootstrap. So what have you?
Yeah. So,
Have you found new asymmetries this way?
I believe that, yeah. So, So
the simplest, just look at triquetizing.
Okay. Okay. So,
Triquetizing, then with the same deformation, this epsilon prime deformation, the ball that goes to 3, degenerate bound state.
okay. So,
Can you solve the S matrix? And sorry, can you solve the boundary quasi matrix and see whether it saturates some of your bounds?
yeah. But yes. Maybe this is not related to the boundary bootstrap. But yeah. So in our paper, we solve this modified boundary Gaussian inversion for for minimal models.
I see.
General P.
I see.
So then the interesting point is that in the case of tri-critical icing case, this modification term is non-trivial, is trivial.
Why?
Because maybe it's good to write down the figure.
Yeah.
But
you're saying D and B are all with this. It has to be the same because
Yes.
of the S matrix.
yes.
I see.
And so that's why the non-trivial modification starts from P equals 5.
I see.
So,
So how does the R matrix look like? You know. In this case?
okay. Then we found that the symmetry constraints from non-invertible symmetries is so strict, and so then the result seems to be very simple.
Can you write it down? It's very simple.
So,
Roughly.
sorry. Please wait. So. Okay, so yeah. So actually that we can split this boundary matrix like and so this part is the off-diagonal scattering. And B and C is different. So this is the so-called off-diagonal scattering, and this is the diagonal scattering.
So they're the same functions.
Sorry. Here is different.
I know, but the U's are they the same functions?
Here.
Yeah, the U.
Yeah. So
Same U.
yeah, same U. But here B is different.
Yeah. Okay.
And so yeah, the function is different.
Okay. No. Are they the same functions? The theta depends.
Yes, theta depends.
Same.
Yeah, same. Okay, so then I derived this part, and firstly we can give the constraints on here from the Ward-Takahashi identities for non-invertible symmetries. So that implies that this is an non-invertible topological line. So we must sum over this one here with must be equivalent to this. So that we assume this the Ward-Takahashi identity. So then one can show that this off-diagonal part must be identical to 0. So then the non-trivial part is here. And okay, so moreover, that we can say that all diagonal scattering elements must be the same. So Then the non-trivial part is just a simple U.
I see.
So yeah, this is so strict condition on boundary scattering. Okay, so then after plugging this into the several process functions, and then we obtain but here the FB is quite quite not trivial and
P is parameterizing the P in the model.
yes, right. Yeah.
But has this quantities FP has they appeared before? Once you have reduced to this.
Yeah. So also the thermal papers.
FP already appear there.
Yes, right. Yeah, so
So this is from plus 1,3 deformation.
yes, right.
Okay. I see. So nothing so simple.
Yeah. But yeah, so we check that this boundary matrix satisfies this modified boundary.
I see.
Just some integrability in the cross in the completeness part, but the first relation, the R equal different R, that your derivation which applies really to this R different R, there's no integrability, right?
Yeah, right.
Integrability, so okay, because you want to solve some crossing completeness equation.
Do you have any comments on how this applies to the monopole problem? You had it on your slide there, so I'm not allowed to ask, I guess.
Yeah, I'm not sure the concrete ideas.
Okay.
But yeah, so okay, so yeah, so consider the four-dimensional monopole scattering problem, and we confine ourselves to the S-wave channel. So then this four-dimensional monopole scattering is derived to reduce to two-dimensional scattering. So moreover, assuming the monopole is very heavy. So then as a monopole can be regarded as a boundary. So then as our boundary scattering situation is exactly the same as the monopole scattering. So yeah. So So we hope that our findings.
But it's crossing.
There is already Wilczek, no? Result.
Sorry?
This already Wilczek result when the plastic sculpture with the model, right? The phase Wilczek, right? I forgot. When you scatter from monopole, you get some. Isn't it that you get some non-trivial phase?
I wouldn't be surprised. But which paper?
Some Chairman had a paper about this stuff.
Yeah, Chairman also.
But the original paper now is like 80s or 90s. I mean, basically you have to solve shredding the Dirac equation in the background of a monopole.
Yeah.
Comparing and out.
Yeah.
I mean, I think already. Is there more to expect?
I didn't know if like
Maybe
crossing.
there's maybe a way to cleanly understand it in this reduced setup.
Okay, yeah, maybe one can phrase it in this language. Yeah, that could be actually.
But you don't have integrability, right?
Well, that's what I was wondering, right? There's no integrability, and then also, yeah, the theory there is quite difficult. Like it's supposed to have this 1/r as you get close to the monopole. It's not even CFT or anything,
Yeah,
so I don't know, maybe you were thinking even about this like 2, 3, 4, 5. CFT
3, 4, 5.
or 3, 4, 5, whatever.
Yeah, that's what I was.
Maybe, yeah, is there some,
That's
that's
not-
maybe a simpler place to apply these ideas, I don't
Yeah.
know,
I
but.
got confused with cosmic strings. Sorry, I got confused with cosmic
Uh-huh.
strings. Yeah, sorry. There is something about this. I think people have done calculations.
Did you follow this crossing symmetry for this anion scattering?
I looked at the papers, because
Yeah.
I actually had a friend work on, I think with the Shiraz Manwala, he was.
You had a
on
friend
it.
working with Shiraz, okay.
Yeah,
Yeah. Who was he sort of
Ramon?
name?
Meta?
I think I met, was he at Chicago?
Yeah, he was in Chicago.
Yeah, I think I met
and
him.
we met at KITP.
I see,
He
I see.
worked on this paper, but I didn't, I
Right.
remember it was complicated. But
Yeah, I wonder if
it was nice,
yeah, not the same because it's in
Right.
3 dimension, but yeah, it should have to do with some kind of topological structure associated with these anions
Hmm.
that leads to the modified crossing. And intuitively probably will come from the braiding. I suppose the F symbol will come from the braiding. Because now you have lines in 3 dimension.
Hmm.
Not cross braiding.
Well, yeah, it would be nice, even like monopole scattering or anything like
Oh,
that,
yeah.
any
That's even
non-local-
harder. but
non-local
Yeah,
objects.
yeah, that's even harder.
Right. But yeah, I don't know, in the monopole problem, maybe there's some, do people ever reference crossing? Do people ever reference the cross diagram in this scattering? Maybe, maybe there's some nice way to attack it using this, I
You
don't
mean
know.
the lie down version?
Yeah,
Yeah,
we,
yeah.
generally, it's just, we just view the one, the case where
The
time
time,
runs
yeah, that's
vertically.
right. Yeah.
I don't know, is there any use to doing it this other way? I don't know.
Thanks. Yeah.
thank you.
Nice talk. We can